Hi, I'm Isaac, and this is Karen, and we did our project on machine learning versus manual classification in predicting protein secondary structure. So to start with some background, 23 amino acids make up all the proteins found in nature, and each amino acid has its own set of characteristics like its charge, polarity, size, and based off of those, it'll form different intermolecular interactions. And if you look to the graph on the right, the amino acid string and its interactions determine whether it becomes alpha helix or beta sheet, and then it continues getting structure from there. And we did our project on these first two steps.
So our motivation is that computational protein modeling is integral to developing novel therapies and studying diseases. To the right is an example of a paper that used computational modeling to find a new intermolecular interaction in the dystroglycan complex, which opened up new pathways of therapies for people with Duchenne's muscular dystrophy. So we found that there's a need for a highly accurate and fast prediction algorithm to further this kind of science. Our research questions were: how accurately can secondary structure be predicted from machine learning? How accurately can it be predicted from manual methods? And how do we optimize those parameters in the manual method?
So the data that we used was from Tasmid Hassan. He had PDB IDs, sequences, and then he used the DSSP algorithm, which calculates secondary structure based on hydrogen bonding to assign each amino acid a secondary structure code. From that, we trimmed the PDB ID so that it matched up with the actual protein database better. And we also simplified those secondary structure letter codes to be A, B, and V, because that's all we could get with our manual method. And we also used an amino acid propensity chart from this Fujiwara paper. So the way that the manual classifier works, I'll explain it in this example to the right here. So you start by determining a frame size. So in this case, that'd be 3. From that, you can determine an alpha and beta threshold. Then you look at the sequence and you split it into frames of whatever size you had. Then you look at each frame. So for example, we'll look at this first one. And then you use the propensity data to calculate a score for alpha and beta. And then if alpha is above the threshold, you'll assign it alpha structure. If beta is above the threshold, you'll assign beta. And if neither, then you'll assign variable, which is our V. And it also always checks A first because that's the more common structure.
So with our machine learning classification, it's a similar method where you start with the frame size, break up your protein amino acid sequence into those frames. And then this is where we differ. Machine learning with the decision tree requires hard encoding of our categorical variables. So we do that and store each amino acid in that frame as a positional data in those columns. And then from there, we can pass it through our decision tree classifier to bring up a set of predictions and cross-reference that with our known secondary structures, calculate the error, and do that for all the frame sizes. So our results with machine learning were kind of questionable because if you were to guess randomly, you have a chance, a 66% chance of guessing correctly. And our machine learning platform had an error rate just slightly below that. However, it is very precise with a confidence interval in that light blue color being very thin. And it only took 3 minutes to calculate over 17,000 protein sequences, which would have taken 6 hours with our manual method.
So this is a comparable graph for the manual results. And as Karen just talked about, we had to cut down the sequence size to be only 100 because it takes so much computational power. And you can see that the error is actually a lot lower. And then the confidence interval is a little bit bigger. And then if you look to the right, when we started to change parameters, in this case, we were changing the alpha and beta threshold. You actually don't see any significant changes in either case. So from the parameters that we chose to investigate, we didn't see any changes. The other graphs that the manual method generated were sequence length versus error, which, as you can see by this straight line right across, there's really no significant relationship. So any sequence length is going to have a comparable error. And then the other one was frame homogeneity, which is important because the way that the manual method classifies, it's limited because it can only be 100% accurate if a lot of the frames are completely homogeneous, which is only the case in really small frame sizes, and it drops off significantly when you get up to the upper limits of frame size. So the conclusions that we came to were that the manual classifier appears to work better in terms of error, but it's a lot slower. There isn't any dependence on sequence length or frame size on error with the methods that we used. And the original parameters were optimal, but we also didn't see any changes. So it's sort of a wash in that regard.
So in the future, we want to use different numerical classifiers for decision tree because our current method brings up some problematical relationships with one being more than the other. And instead, we can use propensity values for that. In addition, we want to manipulate other parameters and see if that improves the accuracy or our error for the manual method and explore a kernel approach to manual estimation. In conclusion, that was our project. I'm Karen, this is my partner Isaac, and thank you for listening.